All right, so last time we looked at 8.5 part 1. Okay, remember this week we're in the packet. Okay, so everything, homework, notes, it's all from the packet, not from your book. We're going to continue on in the same section, just part 2. Okay. First thing they mention in this section is, what does it mean for two vectors to be equal? Well, in order for two vectors to be equal, two things have to happen. One, the horizontal components have to match. And the second thing is the vertical components have to match. They do not have to be drawn in the same spot. Right, so let's say I had a coordinate plane, and I had a vector like that. And let's make a copy of it. Those two vectors are equal. They have different initial points and terminal points, but they each have the same horizontal component. They each go right the same amount, and they each go up the same amount. Okay, so that's what it means for two vectors to be equal. Same horizontal, same vertical components. Doesn't have to be the same starting point. Okay, any question on that? All right, so next thing we're going to look at is our third and final way of writing a vector. So we can draw it as an arrow. We can write it with these angle brackets, two numbers with a comma between them. Or we can use what's called unit vector notation. Okay, I don't think this is something you've done in physics, so this it's going to be new, but I don't think you'll find it overly hard. Okay, first of all, remember what a unit vector is. It's a vector that's 1 unit long. And what we're going to do is define two special unit vectors. The first one is going to be called I. Okay, the vector I is a vector that's 1 unit long, and it points to the right. Okay, another special unit vector we're going to define is J. It's also 1 unit long, and it points up. Now, the idea is we're going to take I's and J's, okay, vectors that point 1 unit to the right, or 1 unit up, and we're going to stack them together. And we're going to stack them together to try to build vectors. Okay? You'll need a certain number of I's plus a certain number of J's. Now, if I and J are positive, we're basically limiting ourselves to vectors that are in the first quadrant on the positive x-axis or positive y-axis. Instead of moving to the right, what could I do to I so that I could move left instead? Yep. Yeah, Augustine?
Make it negative I?
Yeah, if you make it negative I. Okay? Negative I would move you left, and negative j would move you down. So now between using I and j, we can go up, down, left, and right. So let's see how this is going to work. Okay, so what I've done on this page is I just drew the vector I, okay, 1 unit long, pointing to the right. I drew j, which is 1 unit long, pointing up. Does everyone have what's on the left-hand side? Okay, what I'm going to do is I'm going to stack i's and j's together to build that vector, the vector 3, 4. So I don't have to start at the origin, and I'm not going to, because then my vectors are going to blend in with the axis. You won't see them as well. So I'm going to start right there. Okay, so we have a horizontal component of 3. So how many of the i's would I need to stack together so that I get a horizontal component of 3? Victoria? How many i's do I need to stack together to get a horizontal component of 3? Yeah, you need 3 of them. Each one is 1 unit long. So if you stack, let's just make 3 copies of it. Okay, stack 3 of them together. There's 1. There's 2. And there's 3. So what I've done right there, that's the vector 3i. Okay, plus, I need to add something on the end of it to get the vertical component. Okay, Kobe, how many of the j's, or how many vertical segments am I going to need
4.
to get that? Yeah, I'm going to need 4 of them. Okay, let's make 4 copies of that. It'd be nice if it just copied it right where you want it, but it doesn't. All right, so we got 1, 2, 3, and 4. Now connect the beginning to the end. Okay, then I'll move it so you can see it. We just built the vector 3, 4. So it's 3 i's plus 4 of the j's. So that's exactly the same as this. Just a different way of writing it. All right, so now using i's and j's, we can go anywhere we want in 2D. Up, down, left, or right. Okay? You could even, if you wanted fractions, you could use 3.5i. If you want to go 3.5 to the right, you can do whatever you want. But how about in 3D? If I just use i's and j's and pretending we were in a 3D plane, could I move anywhere that I want? What do you think, Colt? No, because I and j only give me 2 directions of movement. They give me left and right, they give me up and down. For 3D, I'd also need like coming in and out of the board. Okay? I'd need another vector, okay? Which we'll call k. We'll do that when we get to 3D. All right. So that idea of being able to move wherever you want, okay, that's called spanning, S-P-A-N, spanning the plane. Right? You give me an initial point, you give me a terminal point, I can put i's and j's together and I can get from the initial to the terminal. Any initial, any terminal you want. Right? If you take away me being allowed to use i's or j's, then I can only move in straight lines up and down or left and right. Okay, so you need both of them together. All right, so the next part we're going to look at some things we've already done. We've done it visually, but now we're just going to do it with arithmetic. So we're going to look at adding, subtracting, scaling, and finding the length of a vector, but we're never actually going to draw it. All right, so the first one is adding the vectors. Okay, if we were going to do this like we did last time, you'd have to sketch V, you'd have to sketch W, put it on the end of V, and then draw in the vector from the initial point of V to the terminal point of W. Well, if we want to do it on paper, okay, all we have to do is take the horizontal components, add them up, take the vertical components, add them up. That's it. Okay, for subtraction, very similar. Just subtract your horizontal components, comma, subtract your vertical components. With addition, if you accidentally switch the order, would that be okay or would that change your answer? Emily? Yeah, with addition it doesn't matter, but with subtraction it is very important you do it in the right order. Okay? All right. And next thing is our scalar. Okay? Multiplying a vector by a scalar. Okay, this is very similar to, it's a property from Algebra 1. I don't think our book refers to it as this, but I think it helps to think of it this way. If you put a number on the outside of those angle brackets, Anybody have an idea what property you think you might use? Especially if this was like parentheses. Yeah? Yeah, it's kind of like the distributive property. Just multiply each component by your scalar. Okay, remember, scalar is just a number. If your scalar is bigger than 1, it'll make it longer. Less than 1, it'll make it shorter. And if it's negative, flip the direction. Okay, and the last formula is to find the magnitude. Okay, find the length of a vector. Does anyone remember what formula this is very similar to? There's a theorem we already know that we can use to find the length of a vector. Yeah? Yeah, it's really just the Pythagorean theorem. Okay. Look at the example we just had. If this side's 3 and this side's 4, and you want the length of the hypotenuse, think of it as a right triangle. And use the Pythagorean theorem. So square one leg, square the other leg, add them up and take the square root. And that's where this formula comes from. It's just the Pythagorean theorem. Right, so we'll go through with some numbers. We'll try all 4 of these. It's going to be a lot faster than having to sketch it, though. Okay, you don't have to do any sketches, especially subtraction. That one was a pain. You have to take W, flip the direction of it, and then do V plus negative W. Okay, we're done with that. Right, what I'll do to try to get used to writing it with I's and J's and using the angle brackets, we'll do it both ways. Okay, I want to make sure everyone's comfortable with either notation. All right, so Andy, if I want to add V plus W, I'm going to start by combining my I components, horizontals. What do I get?
5.
Yep, 5.
-1.
Yep, you just want to write it with I's and J's this time.
5i.
Good. And what about your J component?
-1j.
Yep, you could write -1j, or what else could you put that's a little shorter?
-j.
Yeah, you could just put -j. Perfect. Okay, or if we rewrite it with the angle brackets. Okay, Brianna, how would I write that? 5, -1. Yep. Good. Any question on how we added those up? That's it. Okay, how about Darren? I'm going to subtract V minus W. Okay, what will I get for my I component if I do V minus W?
-i.
Yep, -I. And how about my J component?
Plus j.
I agree, it's plus. And what did you do? Can you just tell me the arithmetic you did? 3.
3 minus -4.
Yes, 3 minus -4.
So it'd be
7.
7.
Okay, or we can write it as -1, 7. Okay. All right, James. This time I'm going to take the vector, multiply it by 3. What's the 3 going to do to it, basically?
You distribute it through the different components.
Yep, we'll distribute it through, and if you were to draw it on paper, what would be the difference between V and 3V?
Be 3 times bigger.
Yeah, this one's be 3 times bigger. So what do we get for V? 3V, I'm sorry. 3V.
6i plus 3.
Perfect. 6i plus 9j. Or Jill, if we rewrite that like that.
6,
6, 9. Yep. Good. Okay, and the last one, find the length, or find the magnitude. Okay, always starts out with a square root. And Victoria, what's going to go under the square root?
2 squared
Yeah,
plus 3 squared.
good. So that gives me the square root of 13. I can't reduce that. If I could, I would. Okay, anytime you can reduce the square root, always do that. If you end up with a square root in the denominator, we need to fix that. I don't think that's going to happen today, though. We'll see. We'll see if that happens. Okay. Any questions on that? All right, so next part has to do with unit vectors. Okay, so remember, if you have a vector with a length of 1, okay, that's called a unit vector. And the idea is, what we're going to try to do here is we're going to find a unit vector given another vector. So what we're going to do is, let's say we were given this one in black. We want to find a vector that points exactly the same direction, but it's only 1 unit long, instead of however long the black one is. Okay. What operation could you do to change that black vector into the red one? Out of the ones we just did, yeah?
You could subtract.
No, that's not a combination of 2 vectors.
Divide. Well, multiply by something by a number less than 1.
Yeah, scale it. Okay, that's a scalar product. So if you can scale the black vector down, or if the black vector was too short, you might have to scale it bigger to make it longer, make it equal to 1. All right? But we got to figure out what to scale it by. Okay? Let's think of some examples with numbers and then what we'd scale it by to make it 1 unit long. Alex, if I had a vector here, let's say the one in black was 5 units long, what would you scale 5 by to make it 1 unit long? 1/5, yeah. Okay. And Cody, if the black vector was 12 units long, what would you scale it by to make it 1 unit long? 1/12. Okay. Or you could say divide it by 12. Same thing. All right. So that's basically our pattern. Okay. You got to first figure out how long is the vector you have. Maybe it's already a unit vector. You don't need to worry about it. Okay. But if it's not a unit vector, to change it into a vector that's 1 unit long, take the vector and divide by its magnitude. If you take a vector and you divide each component by its magnitude, think about what would happen. A vector that's 8 units long, divided by 8, you get 1. 12 units long, divided by 12, you get 1. Or the way Alex said it was also perfect, if you multiply by 1 over the magnitude, that's exactly the same as dividing by the magnitude. Same thing. All right, what we're not doing, though, is changing the direction. Okay? We're taking a vector that we have, and we're just making it longer or shorter. Specifically, we're going to turn it into a unit vector. All right, so I got the vector 3i minus 4j. And I want to find the unit vector that points exactly the same direction as v, but it's only 1 unit long. Colby, what would be my first step to do with 3i minus 4j? Well, what are we trying to find for it? We're trying to find a unit vector, which has a length of how long? 1. Okay. So the first thing we have to do is look at this vector and figure out what its what is. Maybe there's nothing to do here. Maybe the problem's already done for you. How would you know that, though? You wouldn't know that until you take this vector and find its magnitude. Yeah, find its magnitude. All right? If it's 1, we don't have anything to do. If it's not 1, then we have something to do, and we have a formula right above to do it. All right? So let's find the magnitude. Okay, Brianna, how would I find the magnitude of V?
3 squared.
It's going to give me 9 plus 16, which is 25, or 5. So it's not a unit vector, but we know what we have to scale it by now. 1/5. It's 5 units long, so we need to make it 1 unit long, scale it by 1/5. Right, so you can write it as 1/5 times the vector 3, -4, and then do it out. 3/5, -4/5. And that's your answer. Okay, or if you wanted to write it with IJ notation, it would be 3/5 I minus 4/5 J. Okay, any question how we found the length of V, or how we scaled it to make it into a unit vector? All right, so for the rest of the time, we're going to look at the applications. Okay, so we'll look at a couple word problems and see if we can figure them out. Okay, the first one is going to have to do with a velocity problem. So the type of problem it's going to be is you're taking an object, you're going to throw it at a certain angle, at a certain speed. And they'll tell you that. You're going to throw an object at an angle of, say, 30 degrees with the horizontal at 70 miles an hour. Okay, now when we think about throwing an object, okay, imagine that object is traveling in a plane. Okay. What are the 2 directions that the object travels in if I threw something towards someone? Yeah, give me one of them.
Up and down.
Yeah. If I throw an object towards somebody, there's up and down, okay, movement. And Brianna, give me the other one. Yeah, the left and the right is where like the forward, back, depends which way I throw it. Okay, but that's the 2 directions it's going in. All right. Now, for our purposes, we're going to model it as a line. Okay, it's more of a curve. Okay, eventually, when it gets to its highest point, but at least at the very beginning, if you looked at it, it would look like it's traveling pretty straight, okay, for a very short distance. That's going to be the angle we throw it at, alpha. Okay, when we throw it, there's 2 components. There's the horizontal component and the vertical component. Okay, the lines in red, I'm going to represent those as x and y. And technically they're vectors. Okay, and what I want to do is break down this velocity vector, the one in black, into its horizontal and vertical components. Okay, which trig function could I use, sine, cosine, or tangent, to get the horizontal component? Yeah?
Cosine.
Cosine, very good. So it would be cosine of your angle equals. Now, I want to put something in the top and the bottom here, but I don't want the actual vector in the top and a vector in the bottom. I just want to know the what about the vector. I only care about one thing about it in this picture. Wait, how about Alex? What am I concerned with here about the vectors? I'm going to use two of them, but I don't want the actual vector here. I just want its magnitude, right? Because all we're trying to do is find components. Okay, we just care about the magnitude. So I want adjacent over hypotenuse. And now I'm going to solve that for x. Okay, so the magnitude of that vector is going to be magnitude v cosine alpha. Right, now we'll set it up again. Except now I want to find the vertical component. Cody, what would be the trig function I'd use to get at the vertical component? Sine. Yeah, we're going to use sine. Sine of my angle equals opposite over hypotenuse. So it's the magnitude of y over the magnitude of v. And do the same thing. Get magnitude y by itself. Okay, so Kobe, what's the magnitude of y going to equal?
The magnitude of v times sine.
Anything else? Alpha. Yeah, good. Now, if you add those two vectors together, take the horizontal, take the vertical, add them together, you get the one in black. And that's going to be our formula. All right, so the horizontal plus the vertical and then adding them together gives us our velocity vector. Now they each have a magnitude v in common, so we can factor. You know what, let's write it this way to start. Instead of I'll put the plus sign in when I write it with I and j. But for now, there's your horizontal, there's your vertical. Or you could factor the magnitude of v out in front and treat it as a scalar. Cosine alpha, sine alpha. Okay, so this is one way to write a velocity vector. Or you can write it with I and j. You still leave the magnitude factored out in front, except this becomes cosine alpha I, that's the horizontal, and sine of alpha j, that's the vertical. It's exactly the same thing, just one uses angle brackets, one's using I and j. The second way is how your book does it. But either way is fine. Okay, so any question on that? So this is a velocity vector. Okay, now that we have the formula, all we have to do is look at a problem, and in the problem, they'll always give us the magnitude we're throwing it at, that's your speed, and the angle you're throwing it at. Okay, this is the formula you just copied down, so you don't have to copy it again. And as I just said, we're going to give you an initial speed and the angle you throw it at. So alpha is your angle. Magnitude of v is your velocity. Or your, actually I could just say speed. Okay, so any questions on the formula or what the magnitude of V, or alpha stand for? Okay, so in this problem, it says, suppose you throw an object at 50 miles an hour at an angle of 30 degrees, find the velocity vector. They ask us to specifically write the answer in unit vector form, that's I and J, and explain the meaning of each component when we're done. All right, so Andy, what's my initial speed? Yep, 50 miles an hour. And Victoria, what's my angle that I'm throwing it at?
30.
Yep, 30 degrees. Does everybody have what's on the left? So follow your formula. Cosine alpha I, that's the horizontal. Sine of alpha J, that's the vertical. Okay, now just do it out. Okay, that 50, as I said before, treat it just like a distributive property. It's like a scalar. Okay, so the cosine of 30, that's 0.866. I'm not even going to round it. I'm just going to take that and hit times 50. So you get 43.30. It's the horizontal component. Plus, okay, the sine of 30, if you do that out, it's going to come out 1/2. Times 50 is 25. There's our velocity vector. When we have to combine vectors together and find a resultant vector, the best way is to always write it in unit vector notation. Then you have your horizontal component separate from your vertical. You don't have to think about these angles. Okay? So for a final answer, you never want the angle in the final answer. Just a horizontal and a vertical component. All right, so now I want to explain the meaning of each component. What is that 43.30? What does that represent in terms of throwing this object? James?
How far right?
Well, so you're saying it's a distance?
Yeah.
Well, remember, this is velocities, and these are components of the velocity. So these are speeds. The 43.30 and the 25 are both speeds. If you were to take a radar gun and point it at it and check it, it would say 50. That's what the radar gun would come back and tell you the speed is. But what does the 43.30 represent? It's a good guess, but yeah.
The initial horizontal speed.
Yes. That's said very well. So that's your initial horizontal speed. In this class, we would assume the initial horizontal speed and the final horizontal speed are the same. Technically, that wouldn't be true because of air. Okay? It would slow down a little bit horizontally. But if we were in a vacuum, okay, we could still have gravity, but just no air. The initial speed in the horizontal direction would never change. Now, what about the 25? Alex, what do you think the 25 is?
The angle?
Well, again, these are both speeds.
Wow.
And we got rid of the angle. The angle was 30 degrees. Think back to that idea, if I throw something to you, the object I'm throwing at you, it's moving in two directions. It's moving,
Vertical speed.
yeah, this is the initial vertical speed. What happens to the vertical speed the second this object leaves my hand in the presence of gravity? Oh, Bria? If you're throwing something in an environment where there's gravity, what happens to the vertical speed the second it leaves your hand? it's going to slow down. Okay, so the second this object leaves my hand, it's traveling at 25, I think this was miles per hour. Well, it's going to start slowing down. And we could figure out when it hits its highest value and what its highest value would be. As long as you know the acceleration due to gravity, which is 32 feet per second squared if you're doing feet in seconds, or 9.8 meters per second squared if you're doing metric. But knowing that and the initial speed, you can find out how high this object will go. You can also figure out how long it takes to get there. Okay? And in this case, time up equals time down. So however long it takes for it to get to its highest point, that's how long it takes for it from the highest point to fall back down. So then if we know how long the object is in the air for, and we know our horizontal speed never changes, we could find out how far it goes. Okay, let's say this is in the air for, just 10 seconds. Well, just using very simply distance equals rate times time, because this speed never changes, 43.3, you could find the distance. The tricky part is this is miles per hour, so you'd have to change seconds to hours. But that would be getting into more physics and kind of Newtonian mechanics kind of stuff. Very easy to do now that we have this vector. Okay, any question on finding the vector? All right. So our next application is static equilibrium. This one's a little harder. Has anybody done this in physics? No? All right, well, if you kind of break down that word, static means not moving, equilibrium means balanced. So we're talking about an object that's not moving, it's at rest. And all the forces acting on it are zero. If the sum of the forces acting on an object wasn't zero, it wouldn't be at rest. It would be moving. Okay, and what we're going to do is look at an object that's being suspended from two cables, not necessarily cables of the same length. And we're going to find the tension in each cable. First thing that's important to understand here is if you take the tension in the first cable, let's call it T1, and the tension in the second cable, T2, if you add them together, it's not necessarily going to equal 1200. The reason is these cables aren't only pulling up, okay, they're holding the object up, but they're also pulling against each other. Okay, imagine you had a tug-of-war rope, okay, perfectly horizontal. Okay, maybe the rope, they're pretty long, maybe it weighs 20 pounds. Well, if you had 50 people on one side and 50 people on the other side pulling, I guarantee you the tension in that rope is going to be a lot more than the rope weighs. Could be thousands of pounds of tension in the rope. So the tension isn't just dictated by the object it's supporting, but we've got to take into account the horizontal component as well. Okay, so again, think of this as a two-dimensional problem where this object could potentially move up and down and left and right. If all the forces acting on this 1,200 pounds are balanced, and it's not moving, then we know that the force acting to the left must be the same as what? If it's not moving. Darren? Think of it as like a tug-of-war. If the force pulling to the left is equal to what, then it would not move. Well, not necessarily zero, because there is this force pulling left is actually going to be a number. Imagine I were to cut cable T2. All of a sudden this thing would swing to the left. So there is a force pulling left, but it's balanced with the force pulling. It's not moving horizontally, right? Darren, in this case, it's not moving left or right. So if it's not moving left or right, then the only way that can happen is the force pulling to the left and the force pulling which other way is balanced. To the right. If this doesn't happen, you have movement horizontally. Okay? If the forces are balanced, it won't move left and right. Okay. And Jill, what other direction did we say it's not moving in?
Up or down.
It's not moving up or down. So the force that's pulling it up is equal to the force pulling down. Okay, now we need to try to sketch some of these forces. Okay, basically what's going to happen, now we've got the background, okay, of what we need to do. We're going to set up a couple right triangles. We're going to use right triangle trig to break up the components in tension 1 and tension 2. And we're going to set up two equations. Each equation is going to have two variables. So it's going to be a system of equations, which we then need to solve. All right? So let's start to sketch what's happening. Okay, so we have a force pulling left. And we also have a force pulling right. We have a force that's pulling up and another force that's pulling up. If you add the red and the green arrows together, you get the ones in black. Okay, now we're going to give names to all four of those arrows. Let's call the first horizontal force x1. The second one is x2. First vertical force is y1, and the second vertical force is y2. Now we're almost ready to start using right triangle trig, except we don't have any angles inside the triangles that we want to work with. We've got some angles outside. What would this angle down here have to be? Based on what was given. Emily?
30 degrees.
Yeah, how'd you figure that out?
For the top angle, you have to subtract 90 from 30.
Okay, yep, so this,
60.
good, that one's 60, yep.
And then you add 60 plus 90, and you get 150, and then you subtract 180 from 150, you get 30.
Yeah, so that's perfect. You can figure it out that way. You can also use the fact that you have parallel lines here cut by a transversal. So think of the ceiling and the red arrows as parallel. The transversal is T1. Alternate interior angles are congruent. Okay. I'm going to do that same idea here. The ceiling and x2 are parallel. I have alternate interior angles. They are congruent. All right, so now our goal is to come up with four formulas. One for x1, x2, y1, and y2. And we're going to use T1 and T2 in the formulas. Think of T1 as your hypotenuse for the left, T2 as your hypotenuse for the right. All right, so my force acting left, that's x1. My force acting right, that's going to be x2. We need to figure out that equation. And now my force acting up. Hey, Cole, what's my force acting up here? Yeah, y1's acting up. And y2. So how would you represent the combined effect of them both acting up? Great. y1 plus y2 equals, that's my force down, 1,200. So now let's start to set up our equations. Okay, let's start with the triangle that has x1 and y1. Okay, Augustine, which trig function could I use that would involve the 30 degrees, x1, and my hypotenuse, t1?
Cosine?
Yeah, cosine. So the cosine of 30 degrees equals the side adjacent, which is x1, over the hypotenuse, which is t1. Now I want to solve for x1. Okay, Jill, if I solve that equation for x1, what would I get?
T1 cosine 30.
Good. That's one of the four formulas we need to find and then substitute in. Okay, so x1 is t1 cosine 30. Now let's do y1. Brianna, what trig function would I use that would involve the 30 degrees, y1, in t1? Yeah, we're going to use sine. So the sine of 30 equals opposite over hypotenuse. And Darren, if I solve that for y1, what would I get?
T1 times sine 30.
Yep. And now let's see if we can set the other two up just by following the pattern we had for the first two. James, do you see what x2 would be?
The T2
Mm-hmm.
cosine 45.
Good. So it would be t2 cosine 45. And then y2, that would be t2 sine 45. Okay, so we just rewrote all our x's and y's in terms of t1 and t2, which is good because we're solving for t1 and t2. So we need t1 and t2s. Now fill in all four of these formulas into the two equations we wrote. These are our equilibrium equations, saying everything is balanced. So x1 equals x2. So t1 cosine 30 equals t2 cosine 45. And second equation, y1 plus y2 equals 1200. Okay, so y1, t1 sine 30, and y2 is t2 sine 45. Okay, so we have two equations. Each equation has two variables. That's a system of equations. What's one method we can use to solve a system of equations? Anybody remember that? Oh, Kobe? Remember how to solve a system? Probably did it with x's and y's in Algebra 1. Sure. Andy, can you help him out? How do we solve that system? We've done the hard part. The trig part's done, the physics part's done. Now it's basically Algebra 1 to get these answers. Sure. How do we solve that system? Augustine, do you remember? All right. To solve a system of equations, you can use substitution. So you take one equation, you solve it for one of your variables, and then you plug it into the second one. Right? So that's very, very important to know. So I'm going to take equation 1. I'm going to solve for t1. Okay, I'm going to divide both sides by cosine 30. So I get t2 cosine 45 divide by cosine 30. There's a formula for T1. Now, take T1 in your second equation and fill in what you just did up above. If you don't want to use substitution, you could use elimination. I wouldn't advise that here. I think that would get even more confusing. Okay. Now, once I fill in what I'm telling you I'm going to fill in for T1, okay, what's my only variable going to be in the second equation? Victoria? So once I fill in for T1 what I'm pointing at, the only letter in that second equation will be T2. So now you'll have one equation with one variable, which hopefully we can solve. Okay, let's begin. T2 cosine 45 over cosine 30, that's T1, times sine 30. Just extend your fraction bar. Plus T2 sine 45 equals 1200. Okay, now we need to do out this arithmetic part. Cosine 45 times sine 30 divided by cosine 30. Okay, we're going to get just a decimal. Times sine 30 divided by cosine 30. That order that I just typed it in, that's perfectly fine. If you want to type it in differently, as long as you get that, then you're fine. Okay, 0.408. I put the 0.408 in front because usually when we have a number and a variable, coefficient goes in front. Sine of 45 is 0.707. Joe, what do I do next there?
Combine T2.
Yeah, you have like terms, T2, combine them together. So 0.408 plus 0.707 gives me 1.115. Last step, divide by 1.115. And that'll give me the tension in cable 2. So 1200. So it's 1076.23, and that's in pounds. Now that we have the tension in cable 2, the tension in cable 1, that's easy. We have a formula up above that says tension in cable 1 equals T2 cosine 45 over cosine 30. Well, now we know T2, so we just plug it in. So T1 is T2, what was it, cosine 45 over cosine 30. So there's a lot of steps in this problem, but after you set up your right triangles, okay, and set force left equals force right, that's the physics part. Force up equals force down, that's the physics part. And you're done with your right triangles, then it's just algebra 1 from this point down, solving a system of equations. Okay, let's see what we got. So we got 1076.23 times cosine 45 divided by cosine 30. Okay, so it's 878.74. Okay, and as I said, the tension doesn't necessarily total 1200. The only way it would total 1200 is if you had two vertical cables exactly the same length and the weight in the box was distributed perfectly evenly, then each cable would hold 600, 600. But when you start doing cables at different lengths, it changes the tension. All right, so somebody that was buying cable, okay, to hold this amount of weight, they might look at it and say, oh, well, it's 1,200 pounds, each cable will hold 600, so let's just buy cable that's rated for 800 pounds and we'll be safe. Because each one will hold 600 and then we have a couple extra 100 pounds of tension. When really, if you bought cable that could only hold 800 pounds, it would snap. Even though you think you're getting more stronger cable than you need, it wouldn't be strong enough. Any question on that? So that's the really hard one today. All right, let's take a quick look at the last one and see how much of it we'll do. This is going to come up tomorrow, so that's why I'm taking a look at it now. So basically the idea is if you've got, say somebody's pushing down, somebody's pushing to the right with those two forces. The resultant force is what this is. It's the force that represents combining the pushing down and pushing to the right. It's down and to the right. We're going to see this kind of problem tomorrow when we talk about an airplane flying. So the engine's generating a force in a certain direction, and then the wind is going to blow it in a certain direction with a certain amount of force. And we're going to find out how off course is the plane going to get blown. It's basically just combining the velocity vector for the plane and the velocity vector for the wind. That's all that there is to it. Right. So let's see if we can combine these two forces together. Okay, we have two forces. One of them is 25 newtons, one of them is 80 newtons. And to make it simple, we're going to visualize it in terms of x and y axis. Okay, we'll find the resultant force. I'm not sure we'll have enough time to get the direction and magnitude of it. We'll see. But once we have the resultant vector, you guys know how to find the magnitude. That's like the Pythagorean theorem formula. It's just finding the resultant force. That's the part that takes a little bit of time. Okay. Does everyone have up to example 6? Okay. All right, let's start with the first force. Its magnitude is 25 and its angle is 40 degrees. So sketch that out. It doesn't have to be to scale. That's your first force. The 25 degrees, or the 25 newtons, that's like the tension. You know the tension in the cable, so to speak. Right? What you have to find is the horizontal and the vertical. This is really just like finding a velocity vector. If you think of throwing an object at 25 miles an hour at an angle of 40 degrees, that's all you're really doing here, if you want to think of it that way. Right? And that'll help us find our components. So rather than trying to derive a whole new formula, let's just think of it as a velocity problem. Okay? 25 miles an hour at an angle of 40 degrees. Let's find our components. Okay, Brianna, what trig function do we use always for the horizontal? Cosine, good. And for the vertical, we use sine. Now, do that out. So then we don't have to think about an angle or this 25. We're going to find the horizontal and vertical components. All right, so we get cosine of 40 times 25, that's 19.15. Now do sine 40 times 25. $16.07J. Okay, that's my first force broken down into its horizontal and vertical components. It's pulling 19.15 newtons right, 16.07 newtons up. Do the same thing one more time. Our other force is 80 newtons at 110 degrees. Remember, this is 90. So we're going to think of one of them as going negative this time. Okay, so we're at 110 degrees right there. That means that one would be 70. Okay, because together 70 and 110 make a straight angle of 180. Some people might just want to forget about the diagram and think about it as a triangle problem. That's fine too. Okay, how much was it? 80 newtons. Call this x, call that y. Find your components. So cosine 70 equals x over 80. Instead of dividing by 80, I'm going to move it to the other side. There's my horizontal. And my vertical would be sine 70 equals y over 80. And I'm going to move the 80 to the other side. Now I'm going to do it out just like I did up above. 80 times cosine 70, and then 80 times sine 70. Let's see what we got. Now, just remember, when we do it, x is negative, because we're going left and up. Up, y is still positive, but x is negative. So, cosine 70 times 80, and it's going left, so it's negative 27.36. Vertical, still positive. Okay, 80 sine 70. $75.16. All right. So now we've written. Okay, we've written each vector in its horizontal and vertical component form. Let's call this one first vector, second vector, and now combine them. This is going to be the resultant vector. This part's easy. Just take your eyes, add them up. So we have 19.15 minus 27.36. So negative 8.21i. And then we've got 16.07 plus 75.16. We got 91.23J. That's the resultant force. Okay, how would you find the magnitude of it? Well, you take negative 8.21, square it, take 91.23, square it, add them up and take the square root. How would you get the angle? You could use inverse tangent. If you know two sides of a right triangle, inverse tangent will give you the angle. Okay, but I just wanted everyone to see how to at least get the resultant force. All right, so break it into its components and then add them up. Hey, any question on that? So the homework is going to be 25 to 47. That's just odd. Don't do all, just odds. Okay, 55, 57, and 64 and 66. So we'll take a look at that tomorrow, and then we'll also start looking at what's called the dot product.